Thank you very much. This is the first time I've ever used a microphone, so if there's any issues you can't hear me, please just wave. Thank you so much for sticking around today on a very hot day to listen to this extended talk about something that's just become obsessional of mine. So today I'd like to talk to you about eyewitness identification research. So eyewitness identification has spent decades in the dock, and what I mean by this is that eyewitnesses are often portrayed as one of the least reliable forms of evidence in the criminal justice system. But today I'd like to argue that perhaps we've been putting the wrong thing on trial, and sometimes the problem isn't actually the eyewitnesses themselves, it's that we've been testing them using procedures that we don't really understand. And if I'm honest, I think our own research can also be put on trial. We've spent many years comparing different lineup procedures and experiments without really having a theoretical understanding about why those two things might be important to compare and why they might differ theoretically. And I think, and other people also think this in the field, that this has really limited our understanding of what's going on and also limits the effectiveness of the policy recommendations that we can make when we move into the real world of eyewitnesses. So rather than just talking about eyewitness memory, I'd like you to become an eyewitness. So let's just watch this video. Oh, let's see if this works. Does this work? Oh, yeah. Fun fact, he actually forgot what he was writing during that and panicked and was just like, ah. Anyway, now you are witnesses to a really fast-paced, completely dramatic and very low-budget crime. But nonetheless, you are all now witnesses. And that means that you are a super valuable piece of information, form of information for the police. We've got CCTV, we have DNA evidence, but sometimes they can't connect the person who did the crime to the crime. And that's where eyewitnesses come in. So after you've witnessed this crime, you will probably be asked by the police to describe what that person looks like. And then sometime later, days, weeks, months, sometimes years, the police will have apprehended a suspect that matches your description, hopefully, and then put them in a lineup or an identification parade. Now, I'm using those two terms interchangeably. And a lineup would contain the police suspect and a number of other looking people who look similar to the suspect. They resemble the suspect. And it's the witness's job to pick out the perpetrator if they are there in the lineup. Now, if you identify the suspect, that suspect is more likely to be charged and also then more likely to be convicted at court than suspects who haven't been positively identified. So the influence of eyewitness identification is big. Now, this influence of eyewitness identification might be concerning. If we look back in history, we know that people make errors, and we've all seen this in the textbooks. So in the United States since 1989, over 350 convictions have been overturned on the basis of new DNA evidence. This means that there's actual other evidence that proves that the person in prison couldn't have committed the crime. And inaccurate eyewitness testimony played a role in some way or another in approximately 70% of those exonerations. Now, this is just a small snapshot, one country, but you can see why people are concerned about us being reliant on eyewitness memory to kind of inform criminal justice outcomes. But actually, the question becomes, is memory actually inherently unreliable? Or does the reliability of memory depend on how it is handled, tested, and assessed? And this is a paper. Can you see the citations? Yeah. Can you see them? Oh, it's because, do I need to pull it down? There we go. I did not say this. John Wicks said, Laurie Kiss and Ron Fisher said this. And it's a belief I also subscribe to. So I'm going to be arguing that the reliability of memory depends on how it's handled and tested, and that actually helps us then in knowing how we can help the system. So who thinks DNA evidence is reliable? Show of hands if yes. Yes. Cool. I agree. If we have a large amount of DNA, it provides really compelling evidence linking a suspect to the DNA, which can provide really compelling evidence at court. Do you think DNA evidence is reliable if the person that was doing this swab licked the swab before they started, and then they took their gloves off and swiped it on every single chair in here, and then the gun. No, it's no longer reliable, it's contaminated. And this is a point that leaders of the field have been making, that we need to test memory when it's not contaminated, and we need to test it in a way that best enhances eyewitness accuracy. And ultimately, this is a memory test. So how can psychology improve eyewitness identification? We need memory, an understanding of memory to help us. Right. Oh, you were all right witnesses. That's right. So we've had some examples of this in the previous symposium. So now, if you're a witness of a crime, I'm telling you, the perpetrator may or may not be present in the faces I'm going to show you. I'd like you to try and identify the person that committed the crime, or say not present if he's not there. I don't know what we should do here. Show of hands. 1, 2, 3, 4, 5, 6, not present. Yes, correct, not present. I wasn't doing this to catch you out. I was just simply trying to show you what we do in our experiments. Actually, quite a lot of you got that wrong. What we do next in our experiments is we ask, how sure are you? And usually, if you get it wrong, you're quite low confident. So that should have been my next question. So this is what the field of psychology has been doing. To experimentally test different procedures, we give participants in our lab experiments mock crime videos like the one you saw, and we present them either with a target present lineup that contains the perpetrator from the crime, so that's a guilty suspect, target present, or we give another half of participants a target absent lineup that contains an innocent suspect. The point of the target absent lineup is to kind of recreate the condition in the real world where the police have apprehended an innocent suspect and put them in a lineup. What's really important is that witnesses don't confuse guilty suspects and innocent suspects. This is important because lots of you chose fillers in that example, so you chose the faces around the suspect. That's fine. That is a memory error, and it's useful theoretically to understand what's going on, but that memory error doesn't lead to that filler then being convicted and charged and, being in prison. So what we're really interested in our lab experiments is maximizing guilty suspect IDs and simultaneously minimizing false IDs of innocent suspects, which is what we call ability to discriminate innocent from guilty suspects. Now, when I was thinking about this talk, I was like, Melissa, don't go too deep. Stay accessible, stay interesting, but I'm going to have to go deep because the point of my talk is that we need theory. And cognitive theories are going to help us to make predictions in these experiments, to help us to know what to do in the policy arena. So I'm going in there. So we like to think about our tasks as a signal detection problem. So we can think about a lineup task in terms of distributions of memory strengths. So each lineup face has some memory strength value. And faces that have been seen before have higher memory strength than faces that haven't been seen before. So the guilty suspect distribution of memory strengths lies further along this memory strength axis on average than the fillers who've never been seen before. And in our experiments, we can measure the distance between those distributions in target present lineup, so DTP, discriminability within a target present lineup. Now, I should say here, if you went to our previous symposium, I'm talking about fair lineups. So everyone here matches the witness's description of the perpetrator. So it's a fair lineup. And in a fair lineup, in a target absent case, the fillers and the innocent suspects are theoretically equivalent. Neither of them have been seen before. So on average, they generate the same memory strength distribution, or they're just two distributions on top of each other. In any case, the distance between those two distributions should be 0 in a fair lineup. Now, we can have a case where we'd have an unfair lineup, and this would be when the suspect is the only one that matches the witness's description. Travis did a really nice talk on kind of gradations of fairness. Here's the most extreme example. So in an unfair lineup, the kind of theoretical underpinnings is the same in a target present lineup. We've still got two distributions of memory strengths. But where it differs is in the target absent case. Now you've got an innocent suspect that matches memory more strongly than the fillers. And what that means from a theoretical perspective is now we're working with two distributions over here, and the innocent suspect is stronger eliciting higher memory strength than the fillers who've never been seen before. Now, the reason I'm telling you all of this, which is a long-winded way round, is that the key measure in lots of our work in our lab and other labs is this, the distance between innocent and guilty suspects. So over target present and target absent lineups, oh, that was slow, what we want to measure is witnesses' ability to tell the difference discriminate between innocent and guilty suspects, which is what's shown by that DIG there. So this is the critical measure. And we can measure that by fitting theoretical models to our data, and we can also measure it by doing RSC analysis, which doesn't have any of these theoretical kind of assumptions. Now, policymakers don't care at all about this, but nevertheless, I think this theoretical interpretation of lineups is really important to help guide our thinking about when we make predictions in experiments. Without this, I think we can get really, go off track quite easily. Well, I can, definitely. So the key question then that I've been working on for quite some time now is how then can we enhance the ability to discriminate between innocent and guilty suspects? So that's that DIG measure. And one thing that we've been doing for quite a long time is thinking about the fillers. So this is just a recognition memory task of how similar should the kind of distractors, the fillers, be to the police suspect. And when we started thinking about this, we had a really pretty extreme example. So this is from my PhD research, where we were thinking about suspects with distinctive features. Now, if you just look to the person next to you, without being too cruel, is there anything distinctive about them? Because in this example here, I'm talking about... In this example, he's got a massive black eye. But actually, in real life, there's something distinctive about all of us. Glasses, facial hair, moles. In speaking to the UK police, over half of their identification parades are digitally edited to accommodate unique appearances. So, according to the police guidance then, there's 3 different ways that you can accommodate a distinctive suspect and make a lineup fair. One way is to digitally add that black eye onto everyone. Another way is to pixelate it with like a mosaic obscure on the face of the suspect and all the other faces. You can also conceal it with a big black block. And then some places around the world have used these unfair lineups when only the suspect matches the witness's description. So we set out, no one's really compared any of these procedures before, so we set out to empirically compare them. And we used our theory to make some predictions, which I'll come back to in a minute. And we've got this do nothing unfair condition basically as a control condition to see what happens. So in this first experiment, we had participants watch a mock crime video, and then they either saw, after a delay, they saw either a target present or a target absent lineup. We've conducted this study loads of times with like tens of thousands of participants, and the results always look the same, for us anyway. And so today I'll just display the data from our 2016 paper. We've done it with older adults, younger adults, if you see the black eye at the time of the crime or not, all different things like that. But the results always look pretty much like this. So how do we analyse? This is RSC analysis, which I think is another way that we can get our identification literature kind of out of the dock. It's really useful in measuring discriminability, which is the key thing we want to measure, arguably. So we can calculate the correct ID rate of guilty suspects in target present lineups, which is the hit rate, and we can calculate the false alarm rate, so the incorrect identifications of innocent suspects in target absent lineups, and we can plot those at different levels of confidence. And so all of these points are achievable for a given procedure. So Travis explained this earlier. I'm going to do it the opposite way round. So these are all the correct. This is the hit rate and the false alarm rate at 100% sure. This is all the participants, the hit rate and the false alarm rate at 100% sure and 90% sure. And you can keep going until you've got a family of points, until that last point there includes everyone in that procedure. Now, this is really important measure because I keep going on. We want to measure discriminability. And previously in the field, people have potentially used measurements that confound discriminability with response bias, and response bias being just how willing someone is to choose from the lineup. Now, discriminability is the objectively superior procedure because it maximises guilty suspect IDs and minimises them. So that's what we want to aim for, which is why this plot is really important. So this is actually the data from the experiment. So that's the replication condition. We have about 8,000, almost 9,000 participants. So that's a replication condition. And then when I put the other ones on, you can see that the 3 fair conditions, so replication, pixelation, and block, all on top of each other. And then the unfair lineup expands all the way out and further down. Now, this dashed line here is chance, so we want to be as far as possible away from chance. So we would make the conclusion based on this graph that ability to discriminate innocent from guilty suspects is better in all 3 fair lineups than the unfair condition. Now, the unfair conditions makes people pick the suspect more often, which is why the curve expands so much that way. But the key finding of this was that the unfair lineups impair ability to discriminate, and we didn't really know that until we do this type of analysis that people like Laura, Heather, John Wickstead, Travis, and people have used and introduced to the field. So we can compare the lineups statistically by using something called partial area under the curve analysis. So that just measures the bit that we want to compare, and I've just now taken those values and plotted them on that plot. So you can see here again that statistically as well as visually, the PAUC is smaller for the do nothing unfair lineups compared to the other 3, which are the same as each other. The other thing that we often do in our studies is we fit signal detection models to our data, which accounts for all of the identification decisions. And when we do that, these points show the maximum likelihood parameter estimates from the signal detection model. There's no error bars, which has plagued me, because I'm just showing you how the fitted parameters kind of vary across the conditions. But you can see that it's the same pattern as the PAUC results. So whichever way you analyse these data, the results are the same. The unfair lineups are bad. And multiple people have gone on to find this, which is really good. And this other research doesn't use distinctive features, so it's not quite as an extreme example. And it's really interesting because this account, that unfair lineups impair discriminability, is only predicted by one theory. And this theory very conveniently came out just before my PhD, which gave me a framework for everything I've ever done since. So thank you, Laura Vickers and John Wickstead, for doing that. It's diagnostic feature detection theory. So this theory suggests that there are some features on faces that are useful cues to identity, and relying on those cues improves accuracy. So in this example here, a diagnostic cue could be hairstyle because the guilty suspect has got a different hair to the innocent suspect, whereas a beard would be a non-diagnostic cue because it's shared by both of them. Now, theoretically, in an unfair lineup then, it's not clear that the beard's not useful anymore, so people rely on it theoretically, and that impairs their ability to discriminate innocent from guilty suspects. You now mix them up because everyone's got the beard. If you're relying on the beard, it doesn't help you in this task. Whereas if you've got a fair lineup where that beard is matched across everyone, then you can't physically use the beard anymore. The beard, the non-diagnostic feature needs to be discounted from the decision. And that's the theoretical explanation that we kind of predicted in advance and then found, based on our results. Sorry, I just did there we go. So unfair lineups are bad. And loads of research over the past decades have come to that conclusion. In 2020, there was kind of an influential white paper that was written by experts in the field about what we should do about lineup procedures. And one of the things they came to this in here is that in terms of filler similarity is there's a general agreement among experts that a minimal requirement that fillers should fit the description that the eyewitness gave of the culprit. So basically, we should use fair lineups. And I think everyone agrees with that. Ethically and also psychologically, it makes sense. But even with that basic rule in place, I still think there's like a huge amount of work to be done. When a witness when a witness of a crime might first describe to the police what the perpetrator looks like, the police then apprehend a suspect that matches that description. And in many places around the world, the police then trawl through big databases of images to select who the fillers are going to be in the parade. In the UK, they've got like national systems of databases of faces to look through. So the question is, who should they be picking from this big database to go next to the suspect? There's some faces in this here. These are all description matched, they're all fair. There's some faces in here that look more similar to the suspect I'm scared to press anything in case it goes. So maybe this guy, can you see that? Oh, you can't see the mouse. There's a guy over here that looks more similar, and then the guy above him looks much less similar. There we go. He's probably more similar to the suspect, and he's probably less similar to the suspect. But they would both be fair fillers. So who should ID officers pick? How similar looking should the fillers be to the police suspect? And this is something that the field, I think, has been grappling with for quite a long time. And I'd argue it's because we haven't really had a coherent cognitive kind of account to make predictions about what should happen when we manipulate filler similarity. We did a small ID officer survey in the UK, and this was led by my former PhD student, Tia Bennett. And basically, the ID officers in the UK, at least, they prefer highly similar lineups. That's because they're scared that when they get to court, they don't want to be pulled up on anything later down the line in court, for example. There was also so many different idiosyncratic ways of working. People learn on the job of what they think is the right thing to do, and then they pass that on to their colleagues, basically. But surely science knows the answer to this question. It's a recognition memory task. Surely science knows how similar the faces should be. So to kind of get around this problem, Brent Wilson, Travis Hill-Collard, John Whitsett and I, we developed something called the feature matching model that would help us to make and test predictions about filler similarity. Now, I don't have time to go into the model, and Laura just did a really good explanation in the symposium. But basically, it assumes that there's features on faces that match memory, and then you get a 1. There's features on faces that mismatch memory, and they would be a 0, and it's the sum of those familiarity values that kind of give rise to these distributions that I've been showing you all the way along. And the literature to date is really kind of mixed on this answer to this question. Some studies conclude that low similarity fair fillers are better, others conclude that high similarity fillers are better, and then there's reviews that say, oh, medium then, kind of thing. So we really do need to kind of theoretically understand this to get an objective answer to the question. So in one of our experiments then, participants watched a mock crime video and then saw one of 6 types of lineups. They saw a highly similar, so a target present lineup which was composed of fillers that were previously rated as highly similar to the suspect, the perpetrator. Some participants saw a medium similarity lineup which was randomly selected fillers that were previously rated as medium similarity to the suspect. And other participants saw lineups that were composed of fillers that were previously rated as the lowest similarity to the suspect from our pool of potential fillers. Now, when we selected an innocent suspect, a designated innocent suspect, who was from the middle of our pool of faces, so he was rated medium similarity to the perpetrator, and then we have pools of fillers that were rated as either high, medium, or low similarity to that innocent suspect, and that's an important point. So these fillers are matched on appearance to the suspect in the lineup. And so what would the feature matching model predict? So for target present lineups, these are the memory strength distributions that we would predict based on the feature matching model. And it's not that revolutionary here. So here's the memory strength distributions for low, which is L, medium, M, and high similarity fillers. And then the dash distribution is the suspect. So if you're using highly similar fillers, they're competing to a greater degree with the suspect. The overlap of those distributions is more, so they're more confusable. If you're using lower similarity fillers, we're pulling apart those distributions, and you can better able to tell the guilty suspect from the fillers. So what that predicts then is that you should see an increase in the hit rate as you move from high to low similarity lineups, as the distributions move apart. And that's kind of obvious, I think. Now, the really important bit, which kind of boggled us for quite some time, was the target absent case. And so using feature matching terms, we kind of figured out that it doesn't matter what you do in the target absent case, because regardless of whether the fillers are low or medium or high to the innocent suspect, it doesn't change how similar those individuals are to the witness's memory of the perpetrator. So what the prediction there would be is that regardless of what you're doing for low, medium or high similarity to the innocent suspect, the memory strength distribution should overlap. And so you think it's going to make an innocent suspect stand out by using low similarity fillers, but according to the feature matching model, it shouldn't. So we made those predictions, and then we tested it with just one stimuli set, with that one suspect and one designated innocent suspect, and these are the results from the experiment. So those are actually the hit rates and the false alarm rates. We've got like 10,500 participants here, and the net effect of an increase in the hit rate and no change in the false alarm rate is that the ROC should increase when you're using lower similarity fillers. So ability to discriminate innocent from guilty suspects should increase. And that's what we see in our PAUC measures. Kind of hard to tell on that slide. If I translate that into a plot of PAUC, you can see that area under the curve increases as you're using low similarity fillers. And these findings are really consistent with previous work. So there's findings in 1993 from Wells et al. That kind of suggested that using low similarity fillers shouldn't be problematic as long as they all match the witness's description. So these are all fair lineups. And that's what we're finding here. I think Aureat and Fitzgerald also found a similar thing. But I guess the key thing that's helpful here is that we've got this theoretical model to help us understand why that's true. And so that we can be more sure in the results, I guess, that we're kind of observing. And no one really picked up on that since 1993 because it sounded so obscure. Low similarity? No. That's going to put an innocent suspect at risk. And so I think really the kind of theoretical understanding has helped us kind of, maybe a key advance of thinking about this moving forward. Now, I've only told you half the story, and Laura, yours was half the story in yours as well, because that actually, the experiment I just presented was experiment 1 in that particular paper. So this is the high similarity condition from experiment 1, and as I said, in the target present lineup, the fillers are matched on how similar they are to the guilty suspect, and in the target absent lineup, the fillers are matched on how similar they are to the innocent suspect. So this is what we call a suspect match design. That's not how everyone has done it in the literature before, though. Another way of doing this study is doing something called a perpetrator match design. Now, in the target present case, it's exactly the same because the guilty suspect is the perpetrator. So there's no difference here between these two different methodological ways of doing this study. But it makes a huge difference in the target absent case. So now, in this particular study, if we're doing a perpetrator match design, we're picking these fillers based on how similar they are to the perpetrator. So another way to think about this is we've got fillers that are rated highly similar to the perpetrator. We've taken the perpetrator out and we've put the innocent suspect in instead. Now that's theoretically interesting. It's really theoretically interesting, but it's not what the police could ever do. Because the police would never apprehend an innocent suspect and then create a lineup for them based on the appearance of the perpetrator they don't know who it is. So we've run studies like this. It's really theoretically interesting, but it's just a key point here that this isn't going to be useful for police practice. But the feature matching model helped us to think through that theoretically the pattern of results across these two experiments should be the opposite of each other. So this is just a repeat of the previous design, the previous slide. Experiment 1, we're a hit rate increase, no change in the false alarm rate. So we're expecting an increase in the ROC with low similarity fillers. Now the opposite prediction is true of the perpetrator match design. The target absent case at the top is exactly the same across, so you could ignore that. The hit rate we're still predicting is going up. But dangerously now, or dangerously if you want to protect your innocent suspects, which I think we all do, because using this kind of design, when you use low similarity fillers, it starts to make the innocent suspect stand out in memory. And that's why we no longer have one distribution, we've got now 3 memory strength distributions. And then the specific prediction of the model then is that the false ID rate should increase as filler similarity decreases. And that's the result for those studies. So this experiment 1 is the one I've already spoken to you about. So we're getting better with low similarity. But when we ran experiment 2, the results were as we predicted again. The opposite is true. So now low similarity is now bad. And it was really thinking about this theoretically that helps us to understand this pattern of results. People have mentioned this before in the literature, but now we kind of have an understanding of why this pattern occurs. So we've briefly spoke about this in the symposium as well. So what I've been showing you so far are simultaneous lineups of photo images. Now that's not what the police do in the UK. In the UK, is this going to play? we use video lineups, which show each person from the front moving their head left, moving their head right, and then moving it back to the front. And the witnesses in the UK have to view a sequence of 9 images, 9 different people, and they have to see it twice before they can make an identification decision. So when we go, I do a lot of work with the UK police and kind of like pulling together literature to help them decide what they should do in practice. And if you ever go to them with a lineup study that was done on a simultaneous photo lineup, that's not what we do, so we know it's not useful. Now, there's no theoretical reason at all why the filler similarity predictions should change here, but it is an empirical question, and it's one they want to see answered. So Tia Bennett, who's a former PhD student, Dr. Tia Bennett, embarked on a PhD with the National Viper Bureau, who's the service that provides half of the UK police forces. And we've got an ID booth at the University of Birmingham, where we capture the images that look like what they capture in real life. So she set out to basically do exactly the same study that we've run before. We're doing a suspect match design because that's what the police care about. And the results are a bit wobbly here because we've got 4,500 participants. As you can see by the error bars, the false ID rate's so low that the RSCs are quite wobbly. But low similarity is still coming up descriptively best, but it's not statistically significant. And then when we fit our models to the data, it is in the predicted pattern of results. So it doesn't matter if you use your simultaneous lineup or your video sequential lineup, like in the UK. It suggests that the recommendation for practice should be something like, from a pool of description match fillers, select fillers that are dissimilar to the suspect. And this is one thing that we could take to the police if there's further replications of this effect, which I will come back to later as well. So is there anything else that we can learn from using this feature matching model? So think back to when I've been at the beginning when I was talking about distinctive features, that extreme example. Well, actually, the feature matching model can help us to make predictions about exactly how we can replicate features on faces. So with a former PhD student, Dr. Georgia Harris, and a master's student, Alina Mahmood, we kind of set out on examining different ways in which you can replicate features in lineups. And like I say, this sounds so niche, but over half of the parades are edited in these ways, so it's really important that we get this right. So when you replicate a distinctive feature in lineups, you can replicate the exact same feature over the faces. So here's one of our stimuli sets. He's now got like a tribal tattoo on his face, and everyone's got exactly the same tribal tattoo. It's high similarity. But you could replicate a distinctive feature that's within the constraints of the witness's description, so it's still fair, but is different across the faces. I don't know how clear that is, but everyone's now got a different tattoo. And of course, in our experiments, we've got our unfair lineup control condition, where only the suspect has the tattoo and no one else does. We then selected an innocent suspect who was, again, rated as kind of medium similarity to the perpetrator. He has a different tattoo, which is kind of what you'd expect happens in real life. He's got like a star tattoo on his head. And then we've created lineups that were high similarity replications, so the exact same star tattoo, or low similarity, so everyone's now got a different tattoo. And then we've got our unfair control condition. So participants in our experiment saw one of these 6 different types of lineups. And again, the key point here is that this is technically suspect matched because we're making our target applicant lineups to the suspect. And the feature matching model makes the same predictions that we did previously. Basically, low similarity replication should increase the hit rate, but not affect the false alarm rate, which improves ability to discriminate innocent from guilty suspects. So that's what we set out to test in this particular experiment. So we have like almost 5,000 participants. They're all collected online. And here's that's very blurry. Here's the ROC for that experiment. So the white circles are low similarity, grey is high similarity, and the black is the unfair lineup. And as you can see, again, the low similarity replication is on the highest ROC, as predicted by the model. And there's just the PAUC values put on the plot for you, so you can see they do statistically differ from each other. So again, the recommendation here would be, well, the lower similarity replications seem to be boosting performance. So just looking at those two, comparing the high and low similarity replications, low similarity seems to be giving a boost. And that's the same when we fit our models to the data. Now, this came after the PNAS paper where we compared our two different types of perpetrator matched and suspect matched. So it felt complete that we needed to do the perpetrator matched version of this experiment, which is theoretically informative but not helpful for the police. And when we do that, these are just the PAUC values, you can now see that, it's the complete opposite pattern of results, which is what we predicted in advance using our model. So the model is really useful at helping us to make and test these predictions. And it's really helped us to think through methodologically what we should do in our experiments and how that would impact the results. So if those results are replicated by other independent labs, something we could be telling the police would be to, when you're replicating features, you replicate them within the constraints of the witness's description, but otherwise you can make them similar to the suspect's feature. And again, the UK police want to see this in kind of their own stimuli, and we're currently doing a project again with Viper, West Yorkshire Police and Avon and Somerset Police, where we have provided the perpetrators and they are digitally editing all the images in the way that they do in practice. We've also got they can do moving concealment, but they can only do still replications, so that's another factor to consider in this design. So this is in collaboration with the current PhD student, Kyra Scott, and a research assistant from Cooney, Chaiwon Lim. So to be continued. So if we keep finding this fair similarity advantage, the question is why is the literature kind of being so confused? Because there's loads of great studies, but the results are just always so conflicting, and it's hard to get a handle on what's going on. So I think the literature's confused because experiments have been kind of conducted without close attention to the suspect matched versus perpetrator matched methodological decision that just seems so small, but makes such a huge impact on the results. So we embarked on a systematic review and meta-analysis, a systematic review of the literature about 5 years ago, which turned out to be a big endeavour. I literally put these plots in the talk this morning as the research assistant sent them to me. So don't ask me any questions because I haven't looked through it properly yet. But so hot off the press. So basically we did a systematic review, we did a systematic search, we found 28 papers that looked at some kind of filler similarity manipulation. And we read those papers so closely, looking at all of the different methodological decisions in each experiment, in each study. Papers had multiple experiments, multiple conditions. And we were looking at the methods to decide what our theories would predict about the pattern of results. Because those methods are really important in knowing which direction the results should go. So we divided the papers into 3 categories. We've got papers that compare fair and unfair lineups, thinking back to that distinctive feature example where someone's just got a whopping black eye. So there's other papers that have done that but without distinctive features. And we've got papers now that use a suspect match design, and they compare lower and higher similarity. And we've got a selection of papers here that use a perpetrator match design of lower and higher similarity. And what I've just done to kind of help kind of summarize this is I'm going to present it on forest plots. It isn't a meta-analysis, but on these forest plots then, we're interested in the DIG difference. So what we did as well is that in the previous studies, many of them haven't used signal detection-based analysis, so it's kind of hard to know what's going on in terms of discriminability. So we extracted all the data and reanalyzed it using signal detection models to estimate that DIG parameter that I've been going on the whole way through. So if we've got a DIG for a fair condition and a DIG for an unfair condition, we can just minus one from the other, and then we've got an effect size of the difference. So on the forest plot here, we've got studies down the side. And for our fair and unfair condition, using feature matching model and also diagnostic feature detection theory that I mentioned earlier, we're predicting that the study should fall on that side of the forest plot because fair lineup should enhance discriminability more than unfair. With our suspect match designs, we've also expecting to see the studies fall on that side of the forest plot. because the lower similarity lineups should be better than the higher similarity lineups. And in the perpetrator match design, we should see the opposite pattern, where the studies now fall on this side. And this kind of has been a bit of a labour of love. And we've had multiple students, Georgia Harris, Holly Shakespeare, Cody Vardish, Heather at the University of Birmingham, and here as well, all work on this over the years. So here's the results for the fair versus unfair comparisons. And you can see that all of them, apart from one, do fall on this side of the plot. But those error bars, man, they're crazy, aren't they? So just the precision in these studies is not great. But you can see that, as predicted, most of them do fall on that side of the plot, as we would predict based on the models of memory. I should also say that we are reading the methodological information in these studies and trying to pick out what people did. So this also might be an interpretation thing that we've kind of, sometimes the details aren't there, or sometimes we've misinterpreted what they've done. But by and large, that's what we would predict based on the models. This is the suspect matched plot. Again, look at those error bars. But most of them do fall on that side. We've got a number of, we've got some repeated conditions from a same experiment, which we probably need to maybe combine into one here. So we've got some null differences, which can be explained by the methodological decisions in those studies. But by and large, the results do kind of all mainly fall on the side of the plot that we were expecting. You can see that, so these are in date order, and you can see that as we get from oldest to newest, and we are kind of getting a bit more precise with our estimates as sample sizes are increasing in our studies. And then if you compare that to this perpetrator-matched selection of studies, you can see they do predominantly fall on the other side of the plot, as we predicted. Again, we've got a couple of outliers, which I've highlighted in red, which we'll probably go back to the studies to figure out what's going on. It could just be the natural variation when we're doing these tests anyway. So perhaps the inconsistent findings across the literature are not actually as inconsistent as we previously thought. And the only way we got there is by being obsessive about the theory that was making our predictions and the methodological decisions that were feeding into that. Thank you. So for the police, this kind of reiterates the point that we found in our previous paper, that potentially from a pool of description match fillers, select the fillers that are dissimilar to the suspect. So in those suspect match designs, that's the one we need to be telling the police, the practitioners about. Now, you're probably thinking, oh my gosh, it's so hot. That's enough feature matching for today. But I just have one final thing that I would like to kind of tell you about, to kind of really show you another way in which thinking about this theoretically has helped. So back in 2018, Wickstead et al. Derived 3 competing signal detection models, which kind of outlined how witnesses make decisions in lineups. And these competing decision rules are really useful, because once we know how witnesses are making ID decisions, we can use that to make predictions about what else might help. So this is really kind of crucial, both because like theoretically interesting, but also in terms of making practical recommendations in the future. So to date, it's not really been clear which decision rule best explains what witnesses might be doing in these tasks. So all of the 3 decision rules assume that witnesses pick out the max face, the face with the max memory strength, and they pick out that face if that memory strength exceeds their decision criterion, whatever that might be. But the models differ in how witnesses decide if they're sure enough to pick that person or not. So independent observations models suggest that witnesses will select the max face if that max face exceeds their decision criteria. They're essentially ignoring the other faces in the lineup at this point. They've found their max face and they're going to ID it if that feels strong enough to them. The integration model says something different. So that would say that witnesses, they look at the faces, they mentally compute the sum of the memory strengths of all of the faces, and then they're going to identify their max face if the sum of all the faces is strong enough. Now, that on the face of it is a bit bizarre to me, but it has been a really influential way in which people have analysed their data in this field as well. And then the final decision rule is something called the ensemble model, which assumes that witnesses, again, automatically sum up the memory strengths in a lineup, and then they identify that face if the difference between the max face and the sum of the other faces is strong enough. So essentially that's saying, how much does my max face stand out from the crowd of other faces? And these three decision rules all kind of usually fit the data really well, especially the two-end ones. And the two-end ones, again, also make qualitatively similar predictions in experiments, so it's really hard to decide between the two of them. However, in a paper that was led by Kairos Shen at UCSD, which is John Wixter's PhD student, we kind of used the feature matching model to derive the decision rules, and then we can use that to make predictions about filler similarity. So the different decision rules make different predictions about the effect of filler similarity on DIG, so that underlying measure of theoretical discriminability. So the independent observation model predicts no change in DIG when suspect filler similarity decreases, so no change at all, there's no benefit. The integration model predicts that DIG will decrease when suspect filler similarity decreases, and the ensemble model predicts the opposite, that DIG will increase when suspect filler similarity decreases. And if some of what I've said has been interpretable, you can see that this is what we found when we fit models to the data in the past, and we did a whole lot of model fitting in this paper, and again we find evidence again and again that underlying DIG measure does increase when filler similarity decreases. And that also then gives us a hint that this is possibly what witnesses are doing when they make identifications in lineups. And that is really important information to know, because if we know that witnesses are using this ensemble process, then we can use that to generate new ways of testing eyewitness memory or improving existing ways. Oh, I'm at the end. So what is the point of all this? So we can all agree that the police should construct fair lineups and ensure that all fillers match the witness's description of the perpetrator. Ethically, that's the right thing to do. And now theoretically, we know that's the right thing to do. Other people have found this too. So unfair lineups impair ability to discriminate innocent from guilty suspects, and also make those memory strength distributions overlap more. So theoretically, in the mind of the witness, they're making everything more confusable as well. But the literature currently falls short on being able to give more precise guidance about what the police should do. And I think we can do better than that. So within the constraints of a fair description match lineup, how similar should the fillers be? And so our feature matching model and diagnostic feature detection theory predicts, and our empirical results, I guess, predict that from a pool of description matched photos, the ID officers should be choosing fillers who are dissimilar to the suspect. And perhaps if we're thinking about these unique appearance lineups, we should be replicating distinctive features that are dissimilar, because that increases the hit rate and doesn't put, on average, doesn't increase the false alarm rate. But the main point of this talk, and it's been a long way to get here, is that the research and the practice really need to be guided by formal models of memory to help us to make and test predictions in these experiments. So the feature matching model and the ensemble model are two such examples. There'll probably be, in a few years' time, there's going to be probably better examples again, but we need them. And we need them for our experiments, but we also need them for policymakers, because once we understand what's going on theoretically, we can use that to better enable police forces to use procedures that enhance discriminability. Okay, thank you. So this has not at all been an individual endeavour, obviously. So thank you very much to everyone that has contributed. Just these particular studies that I've presented today, obviously part of the fun of academia is being able to work with people who are, you know, not only incredibly clever and talented, but also fun and nice people. So yeah, thank you to all of the collaborators that have contributed. Thank you.